Lesson number 14, daily summary. In this lesson, we solve word problems using the Pythagorean theorem, and we begin our exploration of exponents by using certain rules to simplify expressions containing exponents. 1. The Pythagorean theorem states that for every right triangle, the sum of the squares of the legs equals the square of the hypotenuse. In symbols, we have the equation a squared plus b squared equals c squared. Make sure the hypotenuse is by itself in the equation. So just remember the hypotenuse is this thing over here. It's the side opposite the right angle, the 90-degree angle. And the other two sides are called the legs. So A and B in either order. Just make sure that you put whichever one is right here. The longest side, the one opposite the right angle, has to be by itself when you write that equation. Number 2. You are shopping for a home entertainment center and find one at a good price. The space for the TV in the entertainment center measures 17 inches by 21 inches. You are wondering if your 27-inch TV will fit in the space. Will it? Note that TVs are advertised by the length of the diagonal. All right, so home entertainment center has space for our TV. It's in the shape of a rectangle, 17 inches by 21 inches. And we're trying to figure out if our 27-inch TV will fit. And remember that 27 inches is a measure of the length of the diagonal of the TV. So our job here is to find the length of that red line segment. Again, this is the space for the TV. And so we're going to find the length of this red line segment. I'll call it C. And we're going to compare that C, the space we have available, to the 27 inches of the TV screen we're trying to fit in here. And that will help us decide whether or not it will fit. So using our Pythagorean theorem, which I'll write here, A and B are 17 and 21 in either order. 17 squared plus 21 squared. Again, the important thing is the angle opposite the right angle is, the side opposite the right angle is the side that is by itself in this equation. That is the C. Okay, you're welcome to use a calculator here for these calculations, but 17 squared is 289. 21 squared is 441. That's equal to C squared. Add those two numbers up, 730 equals C squared. In order to solve for C, we need to take the square root of both sides of this equation. We're going to formally talk about square roots in just a couple of lessons, but I think most of us have some experience with them from a previous math class. So square root of 730 I will do on the calculator, just so we can get a decimal approximation for how big of a diagonal we have in our entertainment center. So square root of 730 is roughly 27.02. Okay, so 27.02 inches, that's how long we have in our, that's the size of this diagonal space in our entertainment center. So our 27-inch TV, will it fit? I suppose, just barely, right? We've got 27.02 inches and we're trying to fit 27 inches in there, so it will fit just barely. Okay, so that is a very minor topic in our course, Pythagorean theorem. If you see a right triangle and there's information about all three sides of that right triangle, then you are using the Pythagorean theorem. It's a pretty easy kind of problem to recognize when the Pythagorean theorem is the right tool. A much bigger theme in our course, much bigger topic in our course is exponents. That's what we begin right now. Let's shift gears and talk about exponents. Many of the rules for working with exponents follow naturally from the definition of an exponent. Here are some examples of exponents. First one, 7 squared. We know it's 49, but why? Because that 2 is telling you two copies of the number. The number in this case is 7, and exponents are a shorthand way to say repeated multiplication. So it's always multiplication for exponents. So 7 squared literally means 7 times 7, and 5 to the 4th means 5 times 5 times 5 times 5, 4 copies of that number. 2 to the 8th means multiply the number 2 by itself 8 times, happens to be 256 at the end of the day. Just some vocabulary. Exponential expressions are written in the form x to the n, where x is called the base. So the base is that number down there, and then n is called the exponent. That's the number up there. Number 4, it's important we can handle negatives and exponents together. Try the following problems, no calculators. Okay, first part, -4 squared. What does that mean? It means -4 times itself, 2 copies of the number. And we know a negative times a negative is a positive, so this answer is positive 16. In the middle, -4 squared. Some students will see this middle problem is the same as the first problem, and they'll write -4 times -4. That is not correct. That negative in the front really means -1 times. In fact, any negative symbol, you can think of it as -1 times the number. -18 is really -1 times 18. And so because it's -1 times, we know we can follow the order of operations. And PEMDAS tells me that I should first tackle parentheses, which I don't see any. Then I should tackle exponents, which I do see, before I tackle multiplication. So that -1 times is hanging out, waiting for us to do the exponent. And the exponent is only touching the 4. And 4 squared is positive 16. And then that's multiplied by a -1. So -16 is our answer. It's really tempting to give exponents more reach than they truly have. This exponent is not strong enough to reach that negative sign. Exponents are quite weak in general. They only apply to what they are physically touching. In order to get that exponent to reach the negative sign, I need to artificially put parentheses in here. That's the only way to give the exponent longer reach. Okay, last one, -4 squared. The first negative sign is sitting on the outside. It does not multiply by the negative sign sitting on the inside. You can't use our 2 negatives make a positive rule because the negative on the inside is in disguise. It's got an exponent attached to it. So I don't really know what that -4 squared really is until I do that calculation. So we've already done -4 squared. -4 squared was the first part in this table. It is 16. And so the final answer is -16. I'll highlight the things that were equal. This thing is this thing. And then the negative in the front just stays in the front in our final answer. 5, here's our first property of exponents. A to the 0 is equal to 1. In other words, any number raised to the 0 power is 1. I'll say it again, any number raised to the 0 power is 1. That is true as long as the number we're talking about isn't 0 in the first place. That is a minor technicality, but in general, any number to the 0 is 1. So how much is 4 to the 0? It is 1. How much is 5x to the 4th over y to the 17th all to the 0? It is 1. Anything to the 0 is 1, including -3r. But the last one, -3r to the 0, is not 1. Because again, exponents do not have long reach. That 0 is only applying to the r, the thing it is literally touching. The -3 times is just waiting in the front. R to the 0 is 1, but this answer then is -3. Six, the 5 properties of exponents illustrated below are some of the fundamental rules we will use to work with exponents. Carefully analyze the examples and make sure you see why each definition jives with the corresponding example. Okay, number 1. Here's our first property. X to the m times x to the n equals x to the m plus n. Let's see it in action. X to the 5th times x squared. Let's be naive and write out x to the 5th as x, 5 of them right next to each other. And then x squared as x times x. And if I saw this, I would say, well, I don't need the parentheses because it's all multiplication. So ignoring those parentheses, I just see many x's multiplied together. How many x's do we see? We see 7. And so for sure, the final answer is x to the 7th. But the question is, was there some nifty little shortcut we could have done with the 5 and the 2 in the beginning to get us the right final exponent answer? And sure, we just add them together. So 5 plus 2 gives us the 7, and that is our property. So make sure that you see that this becoming this is exactly what this property illustrates in general. X to the m times x to the n equals x to the m plus n. So the properties are in this first column, and the example on the right-hand column is supposed to convince us that the property is true. Okay, let's take a look right here. X to the 5th over x squared. Is there some way to simplify those x's there? So again, being naive, I'll write out my x to the 5th upstairs and my x squared downstairs, and then I will cancel. I can get rid of one x on the top and the bottom and a second x on the top and the bottom, and now the bottom x's are all gone, They've all canceled. So all I'm left with are the x's on top. How many of them are there? There are 3. So for sure, the right simplified answer is x cubed. And then we look at the beginning and we ask ourselves, was there any shortcut we could have done with the 5 and 2 to get the final correct power of 3? And the answer is, you bet. We can subtract. 5 minus 2 is 3. And so that is our property right here. X to the m over x to the n. We just subtract top power minus bottom power, and we're done. Now, you could get away with just that version of this property, but you can see we've put a second version of this property. I think it's worth memorizing separately. It will save us some work. Let's take a look at what happens when we have x squared over x to the 5th, this one. So again, we're just writing all the x's out, 2 of them on top and 5 of them on the bottom, and now we cancel. An x here, another x here, and now we can't cancel anymore. So how many x's are left? Well, there are 3 of them, so it's x to the 3rd. But where are these x's? Are they on the top or the bottom? Well, they're on the bottom, which means I need a placeholder on the top. It's not a 0 up there, and it still needs to look like a fraction, and so our placeholder is an invisible 1. And so our final answer here is 1 over x cubed. And looking again at the original powers, there was a 2 and there was a 5, and how do we get the correct final power of 3? Well, we still subtract just like we did right up above, but in this case the x's end up in the bottom. It's not x cubed like this problem, it's really 1 over x cubed. And why did the x's end up in the bottom? Or how are we supposed to know? In this case the 3 x's end up on the top, but in this case the 3 x's end up on the bottom. Well, it's just a matter of where there are more x's to start with. So if there are more x's on the top, then clearly when you cancel, you will be left over with x's on the top. And when there are more x's on the bottom, yeah, cancel, and there will still be x's left over, and they will be on the bottom. So our new shortcut is that when you see x's on the top and x's on the bottom, you always subtract, but let's subtract in the easier order. That is the bigger number minus the smaller number. So we always end up with a positive exponent answer at the end, but make sure that you put those x's wherever there were more to start with. Okay, property number 3, let's take a look at our example. X to the 5th squared really means x to the 5th times x to the 5th, 2 copies. And then x to the 5th can be rewritten all the way out like that. And then this x to the 5th can be rewritten out with 5 x's next to each other. So how many x's do we see in total? Well, there are 10 of them there. What's our nifty little shortcut here for getting the correct final answer of an exponent of 10? And it's to multiply the 5 and the 2. So when you see x to a power in parentheses raised to another power, you get to multiply those properties. And for many students, this is the first sticking point in this list of properties. This multiplication becomes addition of exponents. It's not multiplication of exponents. The multiplication here becomes addition, but the pattern in this case is multiplication. And so it's really easy to do a property, do something that looks reasonable, but actually is not legal. So you got to be really careful that you are correctly identifying which property is the correct one to apply. Okay, number 4. Let's suppose we have xy to the 3rd. That's 2 things multiplied together in parentheses, all to a power. So writing it out, I see 3 copies of xy, just all multiplied together. Now this is a straight multiplication problem, and so those parentheses are not relevant. And also I can multiply things in any order without changing the answer. So in my mind, I'm shuffling together all of the x's to the front and all of the y's to the back. And this xxx is really x cubed, and yyyy is really y cubed. And so what's our shortcut here? Well, you had xy to the 3rd power, and you ended up with x to the 3rd, y to the 3rd. And so in some sense, it kind of looks like the distributive property where that 3 comes in and hits both of the factors in the parentheses. Both factors get that exponent of 3. I don't want to call it the distributive property because the distributive property is specifically something like 4 times x plus 3, where that 4 distributes to both terms in the parentheses. So I'll call this our pseudo-distributive property. X and y both get the power of m in this property. Okay, number 5 is nearly identical. We're not even going to look at the example. We'll just look at the property itself. So when you have x over y in parentheses to a power, that's a fraction to a power, you get to, again, pseudo-distribute that exponent to both top and bottom of your fraction. So x to the m over y to the m is our pseudo-distributed answer. Okay, number 7 says rip off the first page of this packet, which has a copy of the properties above, plus a number of other properties we'll cover soon. Let's use the first 5 properties to simplify this very complicated expression. So we're not going to read it, but our job is to make that thing as simple as possible, and we are going to use all 5 of these properties from up above, some of them repeatedly. Fair warning, this is a long problem, and in terms of using these 5 properties, this problem is about as hard as it gets, but I would like you to be able to get to a place where you can tackle simplification problems as hard as this one. Okay, so have your ripped off paper right in front of you, and we're going to work through this problem together using those 5 properties. Make sure you're looking at the correct side. There's one side with a bunch of numbers on it. We'll ignore that for right now and go over to page number 2, the back, with the 5 properties above, as well as some others. Okay, so first observation, this is a big multiplication property. I'll highlight there's the multiplication sign. And what we're going to do is treat these 2 factors completely independently and simplify them separately from each other for as long as possible. And then only at the very end will we multiply these 2 things together. Next observation is that inside of the parentheses, we've got a quite complicated fraction here and another one here. And so before we even deal with the exponents, you know, the big squared on the outside of the parentheses and the big cubed, our task is to simplify those fractions internally first. Now, the way that this explanation is written out here in your packet, the left-hand column is the text explanation of what we're doing. The middle column is the first fraction simplified out, like following the steps from the left-hand column. It's all typed out, so that's really just like a read and discover kind of thing. And what we're going to do is the second fraction here in the last column. So let's give it a shot. Step number 1, it says first reduce the numerical portion for each fraction. All right, let's try it. So our fraction is this one, remember? And I said we were going to work on the inside of this fraction only, which means I'm going to copy my parentheses and I'm going to copy my cubed so that I don't forget it. Now we're going to reduce the numerical part. That's the 15 over the 25. So what's the greatest common factor of those 2 numbers? It's 5. 5 goes into 15 3 times, and 5 goes into 25 5 times. So we've reduced the numerical part of our fraction. And now we are going to reduce the x's in our fraction. So we're doing this part right here, reduce the x's. So let's focus on the x's. Here they are, x to the 5th on top, x on the bottom. And so we're looking on that separate piece of paper. Again, we've got 5 properties, and we're looking for one that looks like x to a power on top and x to a power on the bottom. Now in properties 1 through 5, 2 of those properties actually have a fraction in them. And so clearly it's one of the ones with the fraction, but which one is it? All right, again, it's x to a power over x to a power. All right, so take a look. This is multiplication of x's. That's not what I want. Here is x to a power over x to a power. That looks very promising, but let's look at the other fraction one as well. So this one, it's some x divided by some y, all to a power on the outside. It's true, there is a power on the outside for us, right there. But that is not where we are. We are looking specifically just at this x to the 5th over x. No power on the outside. We're not dealing with this 3 yet. X to the 5th over x is property number 2. It's this one right here. And this is our subtraction property. And so we're going to subtract the x's, the exponents, I should say. And so we've got x to the 5th on top and x on the bottom. We need to bring in the invisible 1 that's on that x on the bottom so that we can subtract. 5 minus 1 is 4. I know I'm going to have x to the 4th somewhere, but remember, you got to put the x's where there were more of them. X to the 5th was on top. There were more x's up there. We only had a single x downstairs, but 5 x's up on the top. So when I put my x to the 4th, I put it right there on top. Next up, let's keep simplifying in this fraction. We're going to look at y to the 10th over y to the 3rd. You've got 5 properties on that ripped off piece of paper. Take your time, try to figure out which one this is. Feel free to pause the video and come back when you figured it out. So hopefully we've decided that this is again property number 2. Y is on the top, Y is on the bottom, and we get to subtract those exponents. And 10 minus 3 is 7, and you put those Y to the 7th, you put that Y to the 7th where there were more Y's to start. Y to the 10th, there's more of them upstairs. There's only 3 of them downstairs. So we get Y to the 7th on top. And that fraction is simplified as far as possible. And already, hopefully, we see that it's getting better, right? It used to look like this whole fraction right in here. And now it looks like this, much cleaner, simpler fraction. Okay, next step. Let's actually copy that guy on the next page. I think that's where it goes. Okay, so here we are. This is exactly what we had before on the previous page. And now we are going to take a look at our next property here. So it says we have fractions raised to a power, and we're trying to apply one of the 5 properties that looks like a fraction to a power. It's written out. This is the one right here that we are applying. It's a fraction to a power, x over y to the m. So this is our pseudo-distributive property where the exponent comes in and hits both parts of the fraction. So let's do that. Also want to point out that you have 2 sets of parentheses here. The numerator and the denominator both get parentheses. So fraction, parentheses, parentheses. And inside of those parentheses, we're putting the old numerators and denominator. 3x to the 4, y to the 7, 5. Both in their own parentheses. And then the pseudo-distributive property says that each parentheses gets the exponent. In this case, the exponent is right here. It's a 3. So this one gets a 3, and this one gets a 3. Okay, next up. Says we need to figure out how to bring the powers into both of our sets of parentheses. We do that by applying this rule, x times y to the m. Take a look. Right in here, up on top, you have 3 times x to the 4th times y to the 7th, all raised to a power. And so that is multiplication inside of parentheses with a power on the outside. And of our 5 properties, only one of them fits the bill. It's this one. It happens that there are 3 things multiplied in here and only 2 in here. That's okay. This property right here works for no matter how many things are multiplied in the parentheses. We just get to pseudo-distribute that power to every single one of the factors in the parentheses. Again, I'll point out all of the parentheses. Every single factor in here gets its own parentheses. Let's try it. So this one up above here equals. So we're going to give 3 parentheses up on top. The bottom, there actually isn't anything to do. I'm just going to copy that one. But upstairs, I had a 3, an x to the 4th, and a y to the 7th. Each of them goes in their own parentheses. 3, x to the 4, y to the 7. And according to our pseudo-distributive property, that power comes in and hits both. So each of these 3 things gets the power of 3. That's this 3 right here. Okay, so we're getting there. Let's take a look. The next thing to resolve is this term right here, x to the 4th, the whole thing to the 3rd. That is x to a power raised to yet another power. Look on your properties list, the separate sheet, 1 through 5. Which one is this? Pause the video here and figure out which one, 1 through 5. Okay, hopefully we see that this is property number 3. It is looks just like this because we have x to a power in parentheses raised to another power outside. That's exactly what this thing is here. Okay, so let's go ahead and apply that property, which says we're supposed to multiply our exponents together. So here we go. I'm going to copy my fraction and most of my parentheses here. Okay, so there's the fraction. 3 to the 3rd, no problem there. X to the 4th to the 12th, we said we multiply those exponents and we just get, sorry, x to the 4th to the 3rd, multiply and we just get x to the 12th. Let's take a look at the next one, y to the 7th to the 3rd. Which of our 5 properties is this? Hopefully we see it's exactly the same one, and again we multiply those exponents together. 7 times 3 is 21. Downstairs I'll just copy my 5 to the 3rd. Okay, and then the very last thing to do is to rewrite the numerical pieces, 5 to the 3rd and 3 to the 3rd. Those numbers are easy. If you don't happen to know them, you can look them up on your sheet. But 3 to the 3rd is 3 times 3 times 3, which is 27. I'll just erase it here and put a 27. 5 to the 3rd is 5 times 5 times 5. Let's pause here and make sure we can use the numerical part of the ripped off piece of paper. So flip over to the front of that side with all the numbers on it. If you want to find 5 to the 3rd, I can actually do it here. So if you want to find 5 to the 3rd, because it is a third power, 5 to the 3rd, we are looking at the perfect cubes list. And 5 to the 3rd, we go to the 5 and we read straight across until we get to the perfect cubes list, and there's our answer. 5 to the 3rd is 125. So let's go ahead and put that on the denominator of our fraction. So this 5 to the 3rd is really 125. And so that entire thing, all of this is as good as it's going to get for the second part of our problem. This thing right here is what we started with, and we ended up with this thing. It's typed right down there. We didn't track the first part, but the first part was this fraction, and you can read the middle column of that entire table up above. It eventually simplified to that, which was copied right here. So as we said, we treated these two factors completely separately for as long as possible, but now we've simplified each of those factors as much as we can, and finally we get to smush them together. And we know in order to multiply two fractions together, we don't need a common denominator, we just multiply straight across. And so here it is, just copied straight across, one big fraction. There's a multiplication symbol, there's a multiplication symbol. And now we get to do just one last application of some of our properties here. So let's take a look. 81 times 27, so this is multiplication on the top. And so in my mind, I'm shuffling together the things that go together. So I've shuffled the 81 and the 27 together in my mind. They are multiplied together. It turns out that you just get 2187 when you multiply those two. You can do that on a calculator. But the next one, the one that we're going to focus on, is this. I see x to the 6th on top, and I also see x to the 12th on top, and those are the only x's anywhere in this fraction. And so again, in my mind, they are right next to each other. X to the 6th times x to the 12th. It's all multiplication. So let's figure out which one of those 5 properties from that ripped off piece of paper this one is. Pause the video and figure out 1 through 5, which one is the right one. Okay, so hopefully we've seen that this is property number 1, and in property 1 we get to add those exponents. X to the 18 is good, so x to the 6th, x to the 12th becomes x to the 18 right there. Okay, next up, let's look at the y's. I see y to the 21st up here and y to the 10th here, and those are all of the y's. I'll just write them together in a single fraction. Y to the 21 over y to the 10th. Let's figure out which of our 5 properties this is. Pause the video and come back when you've got it. Okay, so hopefully we see this is property number 2, which says you're supposed to subtract those powers. Now you got 2 choices. You could do 21 minus 10 or 10 minus 21. But if you do 10 minus 21, you have a negative exponent, which at this moment in our course has no meaning. It will very soon. But my advice is to subtract in the order that gives you a positive answer. So we're doing 21 minus 10, which is 11. So I know that the answer is going to have y to the 11th in it. But where do I put that y to the 11th, on top or bottom? Well, there were more y's on the top. 21 of them is more than 10 of them. And so my y to the 11th ends up upstairs. If you want, you have a force of 1 there, so it looks like a fraction. But y to the 11th right upstairs. Okay, and then finally, downstairs, all we have is a 49 times a 125. Again, you can just multiply those on the calculator, and we get 6125. In theory, we should also just make sure that the two numbers don't reduce any further. 2187 over 6125. They don't have any common factors, but it's worth a look. So that last fraction is our final simplified version of the original problem. As I mentioned, this is tough. These problems are hard, but I do want you to get to a place where you can do this level of difficulty of problem.